Good afternoon on the East Coast and good morning on the West Coast. Welcome to today's webinar titled Processing USGS Streamflow Data in R. This webinar is sponsored by EPA's Water Quality Modeling Workgroup. My name is Ben Cope. I'm with the US EPA and I will be moderating today's webinar. Thank you all for joining us today. First, I'm going to briefly summarize some of the features of today's webinar. We hope you will have questions. And please submit your questions in the questions box on your control panel. There will be one break for questions near the end of the presentation. If you have any problems viewing the broadcast, just let us know in the chat box and we will post an answer in that same box. This webinar will be archived for later viewing on EPA's Water Quality Modeling training page. Also, at the end of today's webinar, you will be sent an email with a certificate of attendance. Materials in this webinar have been reviewed by US EPA staff for technical accuracy. However, the views of the speakers are their own and do not necessarily reflect those of US EPA. Mention of commercial enterprises, products, or publications does not mean that US EPA endorses them. The purpose of the webinar series is to help water quality professionals better understand water quality modeling and how models can be used to solve problems facing water quality regulators. Today's webinar is the 32nd in our water quality modeling series. All past webinars have been recorded, archived, and posted to EPA's YouTube channel. Links to the archived files are available on our modeling workgroup website. Further, in a few weeks, a copy of today's webinar archive will be posted on the same website. We encourage you to listen to any of the previous webinars or share access to these files with your coworkers. The target audience for this series is a water quality professional who may want to use, or review models as part of their job, but who do not necessarily have a modeling background. As such, we are assuming that the audience has a basic understanding of water quality science and concepts, but has limited direct modeling experience. Okay, with that, I am pleased to introduce our speaker, Kateri Salk. Kateri Salk is a limnologist and biogeochemist with 10 years research experience in field, laboratory, and data analysis settings. To date, her work has focused on management-relevant water quality issues, including nutrient cycling, harmful algal blooms, and PFAS contamination. She has worked in the academic and consulting settings, leading efforts in fundamental research and management support for agencies including the Environmental Protection Agency, the International Institute for Sustainable Development, and several state agencies. In her previous role on the faculty at Duke University, she managed projects for interdisciplinary teams of 6 to 10 people. Dr. Salk currently specializes in data analytics in the aquatic sciences, including empirical and process-oriented modeling, data management for research teams, course design and instruction, and interactive data dashboard development. So with that introduction, I'd like to hand the floor over to Kateri to kick off today's webinar.
Thank you very much, Ben. Appreciate being here today, and it looks like we've got lots of people in the room, hopefully some friendly faces from the previous webinars in this series and maybe some new faces as well. So looking forward to it. The general goals of this webinar series are to first incorporate reproducible and efficient workflows into our data workflows for water quality modeling. As part of that, we will be acquiring, processing, and exploring common types of data that are used in water quality modeling. And perhaps most of all, we are going to be creating and modifying coding scripts for future use. So everything you'll see today, you'll actually be able to access and download and keep a copy for your future use, which can hopefully be applied for your specific context. Just an overview of the webinar series. We have several different topics. We are finished with topic 1. This was processing water quality portal data in R. That will be archived to the website shortly. Today, we will be talking about processing USGS streamflow data in R. And then in the preceding weeks and months, we will also be holding 3 more sessions in this webinar series for processing NOAA weather data, processing gridded weather data in ArcGIS and Python, as well as watershed delineation. So please stick around. If you like this webinar, we'll have several more to come. For those of you who were present at the water quality session, there is one piece that I wanted to follow up on briefly. If you weren't there, this webinar was basically intended as a basic introduction to using the data retrieval package, which we will also be using today. For that purpose was to acquire and process water quality data. There was some really good discussion at the end and some questions that came up about additional packages that can be used for data processing and quality assurance. I wanted to highlight, yes, there are several packages that can further automate that process. One of the ones that was brought up was the NADA package, which can run a robust regression on order statistics on non-detects to have a more nuanced look at what we might impute those values as. That was just one example of several that we could potentially use to further automate that process. So I wanted to just point out that yes, these are really exciting and important extensions to that type of work. And then to just highlight that, while we got started, there are often extensions that you can move forward with to further complicate your code. A few recommendations just to close that piece out. I wanted to note that with coding and with other things, automation and the capacity for creating those efficient workflows should never be a substitute for really understanding your data. So we should always be taking a very close look at our data that's being downloaded and processed and making sure that the automation that we are running on that code to either process it or acquire it or explore it or model with it is doing the thing that we want it to be doing. So really making sure that understanding our data is the foundation and that never gets substituted for something more convenient for automation. Another just caution for you all is to always check multiple fields in your water quality portal data downloads, particularly for flags and non-detects and things like that. The reporting is not always consistent among entities, so it's really important to make sure that you, again, really understand your data, really look through those spreadsheets that get downloaded and making sure that you've covered all your bases. So hopefully a nice little follow-up. Now we'll actually continue into the topic at hand today. So today we'll be focusing on stream and river discharge, also called streamflow in many circumstances. This is really our sort of base key physical characteristic in hydrology. Just to take us back to basics for a minute, discharge is an order of volume over time. Typically for USGS data, we're using cubic feet per second. So what is our volume over what order of time? You can also use meters cubed per second or liters per second. Those are also some common measures. Just to remind ourselves, discharge in the field is typically, fairly complicated to measure. So we would typically subsection our stream out into these horizontal subsections. For each of those subsections, we would measure one or more velocities within that subsection and then multiply the water velocity by that cross-sectional area and add those all together to actually compute our discharge. So fairly complicated and time-consuming process to actually measure discharge. The nice thing is that we don't always have to measure discharge every single time we'd like to know how much discharge is moving through a stream or a river. So one thing that we can develop is a rating curve. So if we actually go out and measure discharge at a range of discharges, we can also concurrently measure the stage or the height of that water level in the stream or river. And then as a part of that process, we can equate those two relationships, and develop this rating curve so that at any given point, if we know the stage of that stream or river, we would know what the corresponding discharge would be. To further automate this process, we have these great gauges that USGS has put out. And so those gauges are measuring stage at an hourly time scale in over 8,000 streams nationwide. And we actually get to receive those data almost in real time. So on the right-hand side here, this was in my hometown where I'm living now, the Eno River near Durham, North Carolina. We've had some storms moving through recently. So here's our discharge cubic feet per second over the last week or so, and you'll see that signal of those storms that have been moving through. So all this to say, just reminding ourselves of when we're dealing with discharge, we are working with this complex measurement that has been distilled down and automated, and this really nice thing that USGS has provided for all of us to access this really critical physical information about streams and rivers in near real time. So just sending out some appreciation for USGS and just remembering what our basis is for all of the data that we're going to be looking at today. Some common data sources, we won't be going through all of these today. We're going to be going through just some of the basics, but I wanted to highlight some potential extensions if this session interests you and if you'd like to extend some of these data processing and data analysis tools in R. So specifically for hydrology and streamflow, I've highlighted a few of my favorite tools and packages. Again, I just brought up the USGS gauges. We're going to be accessing gauge information from the data retrieval package in R, so you'll see a lot of that today. Specific agencies or other entities may also gather agency-specific information, so you might have more manually collected things like that you can access. The EPA has a StreamCat database, which I'll go through in a minute, that contains information about stream catchments and watersheds to help connect these physical measurements within streams to watershed information. USGS has a stream stats tool with a corresponding R package called stream stats. This allows you to delineate watersheds and compute flow statistics for given points in streams. And then finally, NHD Plus, there's an R package called NHD Plus Tools that allows us to delineate flow paths and catchments as well, which I'll highlight in a minute. These last three, StreamCat, StreamStats, and NHD Plus, these will not be the focus for today, but I just wanted to highlight these as some really exciting extensions if this interests you. So just to highlight a few of those things I just mentioned, again, I mentioned we're going to be using USGS gauge data today. Here are some of my favorite links to gain some information about those R packages, the data retrieval package specifically. Again, this data retrieval package is going to allow us to access the current water data for the nation. So previously, if you had wanted to download these data, you'd want to visit this website and click through and go to those download links. But here we can actually access it remotely and work within our R environment to access that data. The StreamCat data sets, just highlighting this one. So these are several hundred metrics that include information for local catchments as well as watersheds for streams nationwide. There's over 2 million stream segments that are available through StreamCat. I will mention there is a StreamCat Tools R package, but it's still in fairly draft form, so just be aware of that. That might be something to stay tuned on. Some of the functions may work well for you right now, and some of them are still under development. So just wanted to highlight that. This is one of the tools that is up and coming. Stream Stats, like I mentioned, there is an R package to access the USGS Stream Stats API that you would typically access online. You can download this from GitHub specifically, so that's the way to actually access this package. It is not in the R CRAN library of packages at the moment. And then finally, one of my favorite R packages for stream applications is NHD Plus Tools. This can allow us to identify flow lines, flow paths, catchments divides, all sorts of really useful information. That is just the tip of the iceberg in terms of all of the really cool things that NHD Plus Tools does. They've got a GitHub page as well, and I'd recommend starting there. They have some really useful vignettes to help explain the functionality as well as how to implement them within R. So with that, I'd like to direct everybody. We are going to be moving to an R script momentarily. I'll show you how to get there if this is your first time joining us. If this is your second or third time joining us for this webinar series, this should look familiar because it should be the same location that you've accessed the previous information from. So if you visit github.com/katerisalk/ this webinar's link, you should have received this link as part of your registration for the event as well. But if you haven't, you can see it up here on the screen if you'd like to type it in. From this URL, this is a repository for all of the information or all of the resources for this webinar. On the right-hand side of that URL, you'll see a green button called Code. If you click that button, you can also find a download zip folder, and this will download the entire repository where you can access the session information. If you've downloaded this previously, there will be information and resources on session 2 that are included in this zip folder that's downloaded. If you have information and resources from the previous webinar, you can keep those where they're at and just drag and drop the session 2 information into your folder where you have that stored. If this is your first time downloading it, you can grab the whole zip folder. It will include both information from session 1 and session 2. One thing to also mention is I've uploaded the slides for each of the presentations in a presentations folder. So that should show up as well as you're downloading the zip folder. If you've downloaded this prior to about a half hour ago, actually almost an hour ago now, there will be one additional line of code that's included that I've just uploaded. If you're working from a version that had been downloaded earlier, that's totally fine. I'll show you where that additional line of code is. Or if you'd like to download a fresh version right now, feel free to do so. So to access the coding portion for today's webinar, which I'll bounce to in a moment, you are going to open the file that's called EPA Water Quality Modeling Webinars.rproj. This is an R project file. This will open both R and RStudio, so your window where we're going to be working will open. And then within the project file, this will allow you to navigate within a project folder. So I'll show you what that looks like in a moment. So from the Files tab within RStudio, you can navigate to the Code folder and then find the Session 2 folder, and then there'll be one R Markdown file in there that you can access. And again, as soon as I hop over to the R session, I'll show you exactly how to do that. Alternatively, you can just open this discharge session.rmd file for today. That will work just as well. So if you'd like to navigate to that specific file from your file explorer, that'll be just as functional for today. Finally, before I hop over, if this is your first time using R today, when you download that repository, there is a setup folder. I wouldn't recommend doing this as we're moving through because it will take some time, but if you don't have R and RStudio downloaded on your machine, you can work through the setup file within that setup folder to help install the tools that you need. If you don't have the software installed yet, you can follow along on the screen with today's session, and that should be a great introduction that you can follow up later on once you have the software downloaded. All right, with that, I am going to hop over to a different window here so that we can actually access the code for today's session. So I've opened up that R project folder, or you could also access just the discharge session file. So on the lower right-hand side, you should have a Files tab. And if this opens up to the EPA Water Quality Modeling Webinars folder, you can then just click through and navigate into Code, navigate into Session 2 Discharge, and then open up discharge session.rmd. So that should get you where you need to be. Once you click on that file, in the upper right or upper left-hand corner, a markdown file, which looks like this, should open for you. So welcome to our coding session. Here we have both text and code portions. So that's what I love about these R Markdown files, is that we can include informational pieces as well as code, where we can mix those in and have those occurring together in the same file. So we just talked about the importance of discharge data and why we might use it. During the session, here are our objectives for today. We will be importing USGS discharge data into R. We will be automating some very common processing and data exploration steps. We will also calculate some really common derived calculations for discharge data. We'll be calculating flow duration curves, recurrence intervals, as well as base flow separation. And then finally, no R session would be complete without some visualizations. So we will be visualizing both streamflow hydrographs as well as rating curves. So that's what's up for this webinar, and let's get going. For our setup, one thing to note is some of these lines are what we call commented out with a hashtag or a pound sign, depending what generation you're from. If you'd like to run these lines of code, all you need to do is just delete that hashtag or pound sign, and then you can run that line of code. If you do not have these packages installed, or if you're not sure if you have them installed, you can run these lines of code to install the packages tidyverse, lubridate, data retrieval, and lfstat. One thing to mention with lfstat today, and thanks to Marty Kelly from Texas for helping me troubleshoot this today and yesterday. The lfstat package, if you don't have it installed on your machine currently, this package is not supported on CRAN as of about mid-May 2022. So this is sort of hot off the presses. I've been using this package for years. It's really useful for a lot of these applications for discharge data. However, it's not available on CRAN anymore. You can still access the lfstat package, but you need to install it in a different way. So if you don't have lfstat already, what you'll need to do is run that 5th line of code instead of the 4th line of code. So if you delete those pound signs, you can either click anywhere on any of these lines of code, or you can highlight the lines of code that you'd like to run. To run a line of code, you can click Control Return if you are on a PC, or Command Return if you are on a Mac to run those. I already have these packages installed, so I will not be running those lines. And again, if you don't have the package lfstat, you will use this line of code to access lfstat. If you don't have the package dev tools, you can use the same line of code, install.packages, and then dev tools. So if you're not actually able to use this function here, if it tells you that it's not working, you can also say install.packages dev tools. If you run this line of code, the dev tools install this version of lfstat, one thing that it might ask you is which sort of style of the packages you'd like to run. I just clicked 1 and then clicked enter. So if it asks you, click 1 and then click enter. If by chance you are having any issues with installing or accessing lfstat today, I will be running through some workarounds. And so don't worry, don't spend too much time if you aren't able to access lfstat from the beginning, or if you aren't able to install it. I will point out some workarounds as we work through so that you'll be able to participate and still run the code without that package. But like I mentioned, it's a really handy package that I'm pretty disappointed is no longer supported on CRAN for R. So with that caveat, we will continue on. So if you have all these successfully installed, then you'll just run these 4 lines of code that are calling those packages from your library into your current R working session. You might get some warning messages. As long as it doesn't say error, you are fine to keep going. I also have an additional line of code that will set our default theme for the ggplot package as classic. So the ggplot package by default will give us graphs that have a gray background with some hatching on them. I prefer to not have that look in my graphs. Maybe you enjoy it, but my personal preference is to use a more classic background where you have a white background of your graph with no hatching and black axis lines. So setting our theme to theme classic at the start of our session will give us that look. Again, not required, but it's something that visually I prefer, and so we'll set it there for now. Okay, now that we have our setup out of the way, let's actually access some discharge data. So we will be gathering daily discharge data today from the data retrieval package. reminding ourselves that to actually develop an estimate for discharge, we would compare that to our stream stage. So we'll also be gathering stage information and visualizing that rating curve to look at the relationship between discharge and stage. So that's where we're going to start today. Just to remind everybody, if you were here last time, we will be using the data retrieval package again. If you're new to this webinar series, we will be using the data retrieval package, which can access both USGS and NWIS information as well as water quality portal data. My favorite guide or vignette to the package is, the link is right there if you'd like to visit that on your own time. Some basic functions we will be using today are read NWIS DV. This is a read-in daily value data from NWIS. So this will allow us to get our data. There's also a function called what NWIS data, and this allows us to access metadata about a site. So if we want to know information about a site, what data have been collected before, and so forth, the what NWIS data function will allow us to access that information. The example we will be working with today, and admittedly this is a biased look at data, we will be looking at the Eno River in Durham, North Carolina today. That's where I live right now, and so this is sort of my favorite gauge to take a look at now and then, just to see what's happening in my local neighborhood. This code can be easily modified for batch processing if you want to gather information for multiple gauges or for gathering data from a different geographic area. So although we'll be looking at an example from North Carolina today, this code is really easily modified for other purposes as well. So let's go into our second code chunk and our first one that actually deals with data. So we are going to make a new object in our environment called Eno discharge. So again, we're looking at the Eno River and we want the discharge data. That's the naming convention that I prefer to just keep track of my data and my objects of what they contain. We will use an assignment operator. So that's the left pointing arrow within R. This allows us to assign something to this object. We will use the read NWIS DV function to gather information from this specific site number. So I looked this up online to find the gauge number for the Eno River in Durham. We will be gathering two different parameter codes. The first is discharge in cubic feet per second, 00060, and then gauge height in feet, which is 00065. Again, this is something that you can look up from the data retrieval package. You don't necessarily know this off the top of your head. So some internet sleuthing is sometimes necessary to find the exact information you need. Just to be aware, just noticing that these are in imperial units rather than metric units. This is just a convention from USGS, so just keeping track of that if we need to convert things later on. You could stop right here and just say, I want discharge and stage information for this specific gauge site, and if you ended it there, this function would give you all of that information. However, I'd like to trim this a little bit and trim this to the complete water years that are present for this site. So monitoring for this site started earlier in 1963 and went through went through today in 2022. But the most complete water years, which start October 1st and end September 30th. So that will be starting on October 1st of 1963 and then ending, at the end of September in 2021. So you don't have to specify start and end dates, but I find this easy just because I want full water years for this specific application. So let's run that. And again, you can click anywhere on this line and then click Control Return. You can also highlight the entire chunk of code and run that all at once. Notice here in our environment tab in the upper right-hand corner, we now have an object called Eno discharge. It has over 21,000 entries of 7 different variables. So let's have a look at that right now. So we've got an agency that took the information. This is USGS, our site number, which we provided in the code, and then our start or our dates of measure. And notice that since we're grabbing daily data, this is just every day from beginning to end of the start and end dates. One thing that we might want to change the names of is we have these columns for discharge, the discharge code, whether that's approved or something else. And then we have our stage code with the approval code there as well. That's NA for a while, but we do have entries for stage further down. So I mentioned we might want to change those names. We'll do that in a moment. But I also just wanted to point out that we can gather some metadata for this site and the data types that have been taken. So we can ask for the attributes of discharge. We can ask for the variable information, and this will spit it out. In the bottom of our screen, we've got specific variables. So we've got stream flow in cubic feet per second. We've got gauge height in feet, and this is a mean daily value. So that's useful information just to make sure that we've got our units correct. We know that it's a mean daily value and so forth. We can also ask about the site info if we look at the attributes of that object. So here's our information about the specific location of the gauge. And again, I mentioned we're in Durham, North Carolina. We're being monitored by USGS. We even have latitude and longitude if we want to do some mapping eventually. So that can be useful information as well. Like I mentioned, there's also this function called what_NWIS_data, and this can allow us to gather more detailed information about the specific site. So we will call this a new object, and we'll call it site info. Use that assignment operator to use this function what_NWIS_data for this specific site number. I'll go command return to run that line of code, and here now we have a second object in our environment, where if we click on that, we have some more information. Again, this should look pretty familiar based on what we're looking for. We've got the Eno River near Durham. We've got our site number. We've got latitude and longitude. If we scroll further along, we can see that there's a bunch of different parameters that have been measured. These are these parameter codes. Again, you can look these up online if you want to know exactly what they are. And then it also includes information, whether this is a daily value, what sort of statistic it is. So 0003 is mean, and then there's also minimum and maximum that are available. So all sorts of things, and it's just noticing here that we have a lot of different information that we could access, not just discharge and stage, but other parameters as well if we wanted to. We won't be diving into that today, but just so everybody's aware that those are some useful sleuthing that you can do for these individual sites. Okay, let's go back into our code. So I am a big fan of when I'm working with column names to actually have useful information in them. So I'm going to rename columns 4 through 7 of discharge. So I'm saying the names of discharge, columns 4 through 7. This is matrix notation within R. So this is just calling the specific object and then the columns within that object. Let's call these discharge, discharge approval code, gauge height, and then gauge height approval code. So if we run that and then come back into our discharge window, now we notice that these names have been replaced so we actually can read them and understand them. So now that we have everything labeled and we know what's contained in our objects, let's actually look at the relationship between discharge and gauge height. So we will be making a ggplot. This is a graphing tool within R. If you haven't worked with ggplot before, there are all sorts of other graphing tools, but ggplot is a very common and popular one because of your freedom to do some really creative visualizations. So we are going to make a ggplot. This is our function here. We need to supply ggplot with a specific R object. Where are the data coming from? They're coming from discharge. We also need to supply ggplot with aesthetics. What's going to be included in our graph? So in this case, maybe let's make our x-axis gauge height and our y-axis discharge. From there, noticing here, we'd like to continue building this plot. So the way you do that within the ggplot function is you can use the plus sign to say, let's add a layer to the plot. And we keep going with more and more layers. So just noticing here, each line has a plus at the end of it until we finish off the plot. So if we were to just run ggplot with gauge height and discharge without adding an additional layer, we are going to come up with a very nice, very blank graph. So we have gauge height on the x-axis, we have discharge on the y-axis, but we haven't told ggplot how to actually plot the data. So from there, we can add what we call geomes. And so these are the actual information that ggplot will use to make our graph, to actually put data on the graph. So in this case, we'd like to use geom_point. I've just selected here to make the points 50% transparent, just because there are a lot of points that we're going to be visualizing. So that helps to actually visualize points on top of each other. That's optional, but I think it's a nice trick when you have a lot of data to plot on the same graph. Let's keep going with another plus. And then we can say, let's add some labels. So in this case, these are informative labels, but maybe we'd like to put our units on there. So we can say we'd like the x-axis to be gauge height in feet, and then the y-axis to be discharge in cubic feet per second. Again, optional, but makes our graph look a little bit nicer. So in this case, we can see that as discharge increases, our gauge height increases as well. So we have this nice positive relationship. Notice that for the Eno River, this is not a linear relationship. And if you think about the way that stream beds and stream banks are shaped, we wouldn't always anticipate that this relationship would be consistent across streams. So that's why in each case where we have a USGS gauge, there's this individual rating curve that's developed to relate gauge height with discharge. So looking here, this is just an interesting illustration of when we do have those two things together. Here's what that looks like. Now, this is, we can look at this and display our sort of homemade rating curve, but USGS actually has developed the rating curve based on very specific measurements that have been made. So let's actually work through and access that USGS developed rating curve and see how that compares to the actual data from the site. So we'll make a new object called Eno rating curve, assign that to this function. We are going to read NWIS rating. So this allows us to read an NWIS rating curve. And again, we supply our site number, which is the same as what we supplied before. In our environment tab, the Eno rating curve should show up. And so if we click on that, back in our reader window, we have what's called independent, dependent, and then a star column that we won't use specifically here. But just noticing that we've got these numbers in this object where our independent variable is going to be our stage. So in stage in feet, so going all the way from 0.45 feet to 24 feet. And then our dependent variable will be discharge. So this is when discharge was measured, what was the corresponding discharge with that stage. So we can graph that as well. So let's say ggplot, show me a visualization with the data called Eno rating curve. With our aesthetics, we want our x to be our independent and our y to be our dependent variable. Let's put a geom point on there again, and then relabel our axes so that they have the correct units. So looking here, we've got our gauge height in feet, discharge in cubic feet per second. This increases together, noticing that it's not a linear relationship for the Eno River. And if we sort of toggle back and forth between those two visualizations, they look pretty similar. So not exactly surprising, because the information in the first graph was made up of this rating curve that was developed by USGS. So really handy thing to just have a look at the rating curve. Again, mostly we're working directly with discharge data, but I think this is a nice illustration of the basis of these tools that are really rooted in people being out in the field and measuring those things so that we have these nice data tools. Okay, let's continue along. The next thing we will do is we will be computing recurrence intervals. So a recurrence interval is the past recurrence of an event. In this case, we will be talking about peak annual discharge of a given magnitude. So our value of our recurrence interval, this value will be calculated as, and this is our nice markdown tool to look at our equations. So if we take our number of years plus 1, And then we rank each of the peak discharges across the years that were measured. So we'll rank those in order, and then we add 1 because the recurrence interval will be the recurrence of a given event or greater. So that's where our +1 comes from. We can also calculate an exceedance probability. So that's really related to our recurrence interval. So it's just the 1 divided by our recurrence interval. So this is the probability of encountering a discharge event of a given magnitude or greater in a given year. From our rating curve, this is where terms like 100-year flood and similar terms are developed. This is the probability based on past occurrence. So this is not meant to be an accurate forecast, but simply a probability based on what we've seen in the past. This really relies on what we refer to as stationary behavior. So we assume that the patterns of the past are going to be the same as the patterns in the future. This obviously isn't always the case. So we could have development occurring in a watershed. We could have flow diversions. We could have climate change. So all sorts of things could be impacting our assumptions about stationarity. So it's always important to sort of think about those assumptions and evaluate whether they're actually valid in the system that we're studying. So just something to keep in mind, we will move forward with calculating recurrence interval. I know in the Eno River, we have seen an increase in peak flows over time. So we're not exactly working in stationary space, even with the data we're looking at today, but I'd like to illustrate this example. Just one thing to note, the more years that are available to calculate a recurrence interval, the better. Typically, you have to have at least 10 years of data. 30 years is even better. But again, just thinking about how good of data coverage you have and whether these statistics are okay to lean on. Okay, the first thing we will do is add a few columns to our data set. So we're going to create Eno discharge from Eno discharge. This will just be the same object here. We will use the function called mutate. So this will add columns onto our data. And this is the first place where if you don't have a functioning LF-stat package, I will show you the workaround because this function called water year is only available from LF-stat. So if you don't have that, I'll show you in a moment what to do. So in this case, let's add a column for year within the data set and then water year, which again isn't the same as a calendar year. It still works on 12-month increments, but it starts on the 1st of October rather than the 1st of January. So I'm going to run this. If you do not have your LF-stat package, all you'll need to do is just delete everything on this line except for that closing parentheses and then delete the comma on the preceding line. So it should look something like this, where you're only adding year and then you have 2 closing parentheses at the end of the line. If you aren't able to calculate the water year this time, there are some ways to manually do that if you'd like to Google them. But then also you can just substitute in calendar year for this session so that you can actually run through the calculations. It won't be exactly correct since it's working on a calendar year rather than water year, but in any circumstance, you could substitute in year with water year. So that you can actually run through the script if you don't have a functioning LF-stat package. So I will just revert this back. I'm going to be working from water year. Again, if you just want to use the term year from the Lubridate package to work through that this time, you should get very similar output, and then work through that issue at another time. Okay. Just one thing to note, if you do have LF-stat working, water year is always calculated as a factor instead of as a number. So noticing here it says it's a factor. And we can also classify this as numeric. So one funny workaround in R is that we have to classify it as a character first and then as a numeric. So I'm happy to go through that at some point, probably not within the time limit today, but we'll reclassify water year as numeric. And now if we ask for the class of water year, it will tell us it's numeric. Okay, let's go through and calculate our recurrence intervals. So let's make a new object called Eno recurrence with our assignment operator. We will start with the Eno discharge object, And then we will use this term called a pipe. And so this is allowing us to do things in sequence with an R. So discharge, then we will group by water year. Here's where if your LF stat isn't working, you can just delete water and just group it by year. So I'll group by water year, you can group it by year. Then we can summarize the data and say the peak discharge for any given year is going to be the max of the discharge. And then if there are any missing data, if there are any NAs, we're going to remove those. So there might be a day where the gauge wasn't working or something like that, and maybe we have 364 dates that were measured in that year. So all good so far. Then with our pipe, we will mutate on some new columns. So first, we'd like to rank each of those years in order. So from the lowest peak discharge to the highest peak discharge. So we're going to rank them by peak discharge in reverse. We will also compute a recurrence interval. So again, this is the number of water years plus 1. And in this case, again, if you don't have water year, you can just use year. And then divide them by the rank. And then we can calculate our probability to say it's 1 divided by the recurrence interval. So let's run that whole line of code. Again, you can highlight it. You can click anywhere within that code. Now we've got an object called recurrence. And just clicking on that, we've got water year. You might be year for you. We've got peak discharge. And then if you click on this term rank, this will just show it in order. So we've got rank of 1, the peak discharge was 9,900. The recurrence interval is 59. So remembering it's number of years plus 1. So recurrence interval is 59 years. Our probability of that discharge happening in any given year is about 1.7%. Now, if we go to our bottom ranked discharges, our lowest ranked peak discharge was 555 cubic feet per second. This happens on average about once a year, and our probability of encountering that peak discharge in any given year is 98%. So this sort of tracks with what we would expect. Our most common recurrence intervals are happening about once a year, and our really rare ones are happening rarely. So that is handy. Let's just have a look at our water year versus peak discharge. And again, you can just delete this and say year if you had to compute it by year. So just noticing here, we've got all of our years of data. We've got our peak discharge. It's pretty variable across the years. I've done some time series analysis on the Eno River, and it actually turns out that we are seeing higher peak discharges as time goes on. So this system is not necessarily displaying stationary behavior, which could be a topic for another webinar, I'm sure. So that's just a look at the time series in general if you wanted to plot peak discharge. You can also plot the recurrence interval against peak discharge. And so this is how we might think about estimating how often a discharge of a given magnitude might occur. So let's look at Eno recurrence. Our aesthetics will be X is the recurrence interval and Y is peak discharge. Let's make a point. We can put this in log space, so that can be useful for discharge data because we're working basically in orders of magnitude instead of on a linear scale. And then we'll add one thing, and this is a new geom if you haven't seen this before. It's geom smooth, so this allows us to plot a line through our data. In this case, we'd like this to be a linear model line, so a regression line. And we'll say that we'd like the line to be black, and we'd like it to not display a confidence interval or standard error around that line. So in this case, if we look at our recurrence interval, and sorry, this is on our log scale. Our recurrence interval, as we increase in recurrence interval, we go up in peak discharge. Our line of best fit doesn't fit perfectly, but we're hitting a lot of the points in this case, and with not a ton of scatter around that line. So we might think about making a linear model to say, what's our peak discharge with a given recurrence interval? So this is just the line that's plotted here. We're working it out mathematically. We might want to look at that summary of that linear model. Feel free, we don't have a ton of time today to really dig through the results of here, but that's how you'd create a linear model. And from there, you can look at the coefficients of your regression line and say, okay, let me say, what if I wanted to compute what is the discharge for a 100-year flood or a 500-year flood in the Eno River? So you could compute that using these two lines of code from that given linear regression. Again, these recurrence intervals might look different for your systems. So this is just an example of a way that you could think about developing estimates for a flood of a given magnitude, particularly if your data aren't actually getting up to that 100-year flood probability with the observed data. Okay, so that gets us through recurrence intervals. Again, if you have any questions specifically about that, please feel free to post them in the Q&A. But maybe moving on from there, this will be a nice flow into flow duration curves. So flow duration curves, these can be generated from, we were just looking at annualized data, so our peak annual data. We can generate a flow duration curve from daily discharge data. So on any given day, how likely is it that we will see a discharge of a given magnitude? So here's the specific equation for that. So we've got the exceedance probability, and then that'll be 100 times the ranking of all of the daily mean flows with at least 10 years of a period of record. And then again, this is the total number of daily mean flows plus 1. So again, we're looking at a magnitude or greater with that plus 1. Okay, here's how we would put together a flow duration curve. So let's make a new object called Eno flow duration. We're using the same discharge data set that we've been using the whole time. This specific calculation doesn't involve water year at all, so you should be good to go to just work through those without needing to change any code in this chunk. So let's take the Eno discharge. Then, this is again our pipe operator. That just means we are going to continue this analysis in sequence. First, just in order to rank everything, we need to actually not have any NAs in the data set. So we'll drop all of our NAs for discharge. Over the whole course of the measurements, which is over 21,000 measurements, there have only been 38 missing days. So that's a pretty incredible time series of data. Big shout out to USGS for maintaining that. So we'll drop all those NAs and then arrange them in descending order of discharge. So this just helps us with our next step, which I'll go into now. So let's continue on with Eno flow duration. We are just going to basically overwrite this file. So notice how Eno flow duration is on both sides of that assignment operator. We are going to mutate on, so add on a few additional columns, where we will rank our discharges, so our rank, from 1 to the total number of observations. And so this is why it was nice that we arranged these in descending order, because now we can just add a column that just numbers them one after another. So we can go 1 to the number of rows in the data set. Then we can calculate an exceedance probability where we are dividing our rank by the number of rows in Eno flow duration. So there's our exceedance probability. Now, if we have a look at that, so we've got Eno flow duration. Notice how we've got 38 fewer samples in this one than we did in the discharge. And then notice how this is not organized by date anymore. It's organized by increasing or decreasing discharge. So just noticing that it's now in order of discharge instead of in order of date. And then our rank 1, 2, 3, and so forth. This is probably less useful to look at than our peak flow statistics. So let's go back and we'll actually plot this one in ggplot. So let's make a ggplot with Eno flow duration data set. Specify our aesthetics. So we've got our exceedance probability and discharge as our X and Y. Then this time, we're not going to plot every point. We don't need to see all 21,000 points. We can just plot those in a line. So let's plot all of those as a line because they're ordered. We might make our scale on a log 10 scale and then use labs to relabel our X and Y axes. So on that one, we get a really nice curve here where we're plotting the exceedance probability from 0 to 1. So this is basically our proportion or our probability from 0 to 1. We could think about a percentage if you multiplied it by 100. And then this is just looking at our discharge. This is in log space. You could think about plotting it not in log space. See what that looks like. It looks a lot more like an L, whereas if we plot it in log space, we get this nice S-shaped curve. So just interpreting our flow exceedance graph here, there's about a 50% probability that on any given day, our discharge will either be above or below 100 cubic feet per second. This is likely to be different based on whatever stream you're looking at, but for the Eno, we're sitting around about 100 cubic feet per second as our 50% exceedance probability. Below that, our probability gets much higher. You've got almost 100% probability that on any given day, your discharge will be above 1 cubic feet per second. Whereas on the other hand, you've got almost a 0% probability that your discharge will be above 10,000, even above 1,000 cubic feet per second. And again, these are the daily discharge rather than the peak discharge in each year. So a little bit different application, but we're still drawing on some of these same ideas of ranking all of our flows in order. So there was flow duration curves. I'm sure you could do a lot more exploration with this, but I just wanted to show the basics of how to calculate a flow duration curve, and then how to plot something like that so that you could really visualize what those probabilities look like in your system. Okay, I have one more specific application that we want to go through today, and this is on baseflow separation. So if we look at our streamflow hydrograph, part of our streamflow we might anticipate to be storm flow, so overland flow or shallow subsurface flow that are delivering water to our stream or river of interest, perhaps following a precipitation event. The other component of our flow would be base flow. So this is distributed to those slower flow pathways, including groundwater, not necessarily limited to groundwater. We may have some of those more circuitous, deeper subsurface flow points as well. Often snowmelt will be assigned as base flow as well. So if you live in a snowmelt system, our base flow calculations might be a bit different for those as well. So just to be aware, there's some really good literature out there. If you are in a snowmelt system and you'd like to calculate base flow, I haven't specifically gone into snowmelt here because we don't really have a snowmelt signal in this specific stream. Just a couple of things to point out before we actually get into the code. So I'll highlight two packages today. The first is lfstat. If you're having trouble accessing that, it's nice that we have the second package that I'll highlight. But lfstat, so there's a calculation for base flow in this package. It's called baseflow. This uses what's called a smoothed minima method. So basically, if we look at our discharge in a stream over time, local minima will be selected for that specific hydrograph. And then those minima across days, across weeks, will be connected by straight lines to estimate base flow. So you'll see, and I'll show an example in a minute of what that looks like if we calculate base flow with the lfstat package, which uses that smoothed minima method. The eco-hydrology package, which I won't be loading up today, but you can also use this package. This package has what's called a baseflow separation function. So that's the function that you could substitute in if you wanted to use that package instead of lfstat. This uses a bit different of a method. It's called a recursive digital filter method. This basically, instead of connecting those local minima with straight lines, uses a smoothed line to represent base flow. In most circumstances, particularly if you're trying to get a general idea of storm flow versus base flow, these methods will be relatively equivalent. In certain circumstances of stream flow in a given system, or with more detailed estimates that you'd like to make that are a little bit more precise, there would be trade-offs between those two methods. We won't get into those today. I'm also not enough of a hydrology expert to really dive into those specific trade-offs, but just know that those two methods are fairly are drawing off of different assumptions, but will often come to pretty much the same conclusion, particularly if we are smoothing over a given period of time. both of these packages, I've just included the basics of these functions in the lesson today, but they also have these optional specifications that you can tinker around with based on your specific context. So I'd encourage you to look into the documentation for these functions if you would really like to dive in on baseflow separation, just to make sure that you're getting those specifications correct for your system and your assumptions that you're making. Finally, before we embark on the code, I just wanted to mention that the ecohydrology package, which we haven't loaded today, but you could install and load yourself, this uses functions that will what we call mask other functions, particularly in the package dplyr, which is included in the tidyverse that we've been using today. So what I'd recommend if you are using ecohydrology is to load it first as the very first package you load, and then to load other packages within your session. That way you can use the functions for your other packages like the dplyr filter or the dplyr pipe function, some other functions that ecohydrology masks. So you can use ecohydrology with other packages, but I'd recommend loading it first and then loading your other packages next, rather than loading ecohydrology last or after other packages. Okay, let's get going, and I'll show you here. So in this case, if you don't have the lfstat package working, I might recommend watching along, or if you'd like to try out using ecohydrology, you can substitute in baseflow separation wherever it says baseflow in the code. So two options for you today. If lfstat isn't working, you can calculate it using the recursive digital filter method instead of the local minima method. If not, please feel free to follow along, and then I'm happy to troubleshoot any changes to these code if you'd like to do that after the session. Okay, so let's go through and calculate and do some baseflow separation. So again, for any given discharge, we can attribute somewhere between 0 and 100% to baseflow and storm flow. So let's take our discharge object. Let's make a new object called baseflow. We'll use that assignment operator to assign from discharge. Use our pipe. So again, we're doing things in sequence. Our pipe allows us to say then I'd like you to do this next thing. We are going to mutate on some new columns. The first column name is going to be called baseflow _ lfstat. I like to include which method I've used to calculate baseflow separation, particularly if I'm using both, if I'm trying to calculate both methods. So I've just said baseflow lfstat. You could say baseflow ecohydrology or local minima and so forth. We are going to use the baseflow function on the discharge measurement. And then because our flow can be made up of either baseflow or storm flow, we'll know what storm flow is if we just subtract baseflow from the discharge. So that'll be our second new column. Okay, so if we've made that, noticing here, if we go in and click through into baseflow, again, we've got discharge. Noticing here, one thing to note is that the baseflow separation will exclude the first 12 samples because it uses it likes to start taking the mean. It doesn't know what to do with the very first part because it doesn't have a pattern to recognize yet. So it doesn't start until the 13th measurement. So just noticing here, our discharge was 2.7 on the 13th of October. 2.7 cubic feet per second of that was attributed to baseflow, 0% to storm flow. But as we go along, some of it will be attributed to baseflow and storm flow accordingly. That goes all the way through the 21,000 lines. I won't bore everybody by scrolling through that entire thing right now. But we could do that with a graph. So let's plot, let's say ggplot. We're going to plot with the baseflow data set. Our aesthetics are going to be date and then our discharge. So we'll plot our discharge over time first. We are going to use that, so plus, let's make another layer. We're going to use the geom line function again. So we're going to take a line that connects all of our points. It's like a connect the dots without any dots. We are going to make this line gray for discharge. And then let's add another line that will represent our baseflow. So we'll have another geom line. But this time we want to rewrite the aesthetics. So the first one we had discharge as our Y aesthetic. Now let's say we'd like the aesthetic to be the base flow instead of just the discharge. I'll show what this looks like with a logged Y-axis. And then we can relabel the axes. So our labs, our labels will be X equals year, Y equals discharge. So again, this is just to illustrate what our data look like over time. Noticing our total discharge is in gray. It goes all the way up to upwards of 10,000 cubic feet per second. Notice that our base flow in the black is fairly low. It does go up and down throughout the seasons, so that'll be interesting to unpack a little bit. If you wanted to look at this on a logged axis to really collapse some of that upper variability, wouldn't necessarily recommend this in terms of a final output graph, but it's interesting to kind of visualize. So just noticing here, our discharge will go anywhere from, maybe about 1 cubic feet per second up to about 100 cubic feet per second, whereas our total discharge, which the balance of that would be storm flow, goes all the way up to upwards of 10,000. So this is just an illustration. Notice how base flow isn't always the exact same across our data set. So our base flow is fluctuating, but not as much as storm flow. So one thing I'd like to do is just to look at how base flow and storm flow are varying across seasonal cycles in this system. So I'm actually just going to grab the data from 2018 through 2020. Again, if you had the water year function not working, you could just say year. We just want to sort of zoom in. This isn't for statistical purposes. So I'm going to make a new object called ENO 2018-2020 from the base flow. And then we're going to use the filter function to select certain rows of the code that include only the water years from 2018 through 2020. Now let's plot the same graph, but sort of zoomed in. So again, discharge is going to be in gray. And then we'll plot the base flow. In this case, I plotted it as dark red. I think it shows up pretty well. This will be on the log scale for discharge. So let's make that plot. So looking here, again, since it's not 58 years of data, we can actually see what the seasonal cycles look like in this area of the country and in this specific stream. I'm noticing that our lowest flows of the year are occurring during the winter, whereas our highest flows are occurring during the summer. So noticing that we've got these this cyclical nature with all three of those years plotted. We've got some variability across years, but we do have this consistent cycle that happens each year with the low flows occurring in the fall and winter. Noticing here that the base flow is also following that pattern. So our highest base flows are occurring in the summer and in the spring, and then our lowest base flows are occurring in the late fall and winter. So that might be a useful tool, especially if you're working with lots of years of data, if you actually want to really understand the seasonal cycles of what you're looking at. We can also look at this as a specific, individual event type level. So I've identified a specific event that occurred in 2019, somewhere between the middle of July and the start of September. We're going to filter our ENO base flow for those specific dates. And then I'm going to display that again. This is almost the same code as the previous graph, so I'll rush through this a little bit, but just showing here. So here's from July 15th to September 1 of 2019. Whoops, and this x-axis is not correct. So date of 2019 should be our label for that one. But this is really illustrating that local minima method. So noticing how our base flow is kind of following along here, and then we have a straight line drawn from this this storm flow peak here, where the start of the storm flow peak connects to the base of the storm flow peak, and then we continue along with those sort of connecting the dots in base flow. So this is kind of a good illustration with how that local minimum method is calculated and what's actually going on behind the scenes with that specific calculation. Again, you can tinker with the settings to actually adjust how those local minima are calculated and how sensitive the model is to calculating those local minima. So just be aware of that. Okay, we've got a couple more minutes. I just wanted to go through, we could perhaps calculate some annual summary statistics. We might be interested in knowing, in general, in the Eno River, how much of our annual flow is made up of base flow versus storm flow. In this case, if you want to create a summary from that base flow data set, we can group by water year. Again, if you weren't able to use the LF stat package, you could just group by year, or there are other ways to calculate water year manually. Then we will summarize some data. So within a given year, what's the amount of total discharge? Let's say acre feet per year. We're going to take the sum of the discharge, and then this factor of 723.968 is just how we get to acre feet instead of cubic feet per second, and into year versus second. So we can calculate discharge acre feet per year. We can calculate base flow in acre feet per year, and then we can calculate storm flow in acre feet per year. Again, this is just summing all these things and then converting the units. Then we can take the proportion of the flow that's base flow versus storm flow. So base flow divided by discharge, storm flow divided by discharge. And then one thing I think is really useful here is this will output data with like many decimal places, which may not be super useful in our case. So we can say mutate if. So if the column in the data set is numeric, we will round it to 2 decimal places. So let's do a little bit of summary, a little bit of cleanup in there. So if we go into that summary file, we can look at our water year. Again, the first and the last water year will have NAs because of that. It won't use the first 12 and the last 12 observations in the cycle. You could expand your discharge observations if you wanted to make sure that you have a full water year. So just be aware of that. But then we can look at, okay, what's our proportion base flow across the years? And that should be, these two should add up to 1. So 0.34 plus 0.66 is 1. And so forth. Again, perhaps not useful to scroll through a spreadsheet, so let's actually plot that. So by our water year on the x-axis, proportion base flow on the y-axis. So here's what we're working with in terms of what is our proportion base flow each year. So in any given year, we're probably hovering somewhere between about 20% to about 40% base flow in the Eno River. And given how much variability there is in our peak flow statistics, say, this proportion base flow is fairly robust and fairly consistent across years. We get some variability across years, but we're generally seeing a good proportion of base flow in this specific stream. I think I saw no, that question wasn't relevant. Sorry, we can hop back to a question that I thought I saw a glimpse of later. With that, I also just wanted to notice we didn't talk about any low flow statistics today. So there are some things like 7Q2, 7Q10 metrics and so forth. There's some good description of these statistics at this link that I've posted. We won't have time to go through those today with R, but just wanted to note we really focus on those peak flow statistics today, but there are low flow statistics that also might be relevant to your system. With that, I think I will stop with our scripting part of the session. I think we're going to hop over to some questions. So for those of you who have been waiting patiently with a question, we can hop back to those. And I think I'll hand it back over to Ben Cope so he can moderate some of these questions.
Okay, thanks, Kateri. So yeah, now's an opportunity if you want to type a question in the Q&A box. We'll take those questions in. If your question does not get asked and answered today, or you'd like to contact our speaker, Kateri, directly, you can find the contact information on a slide that we'll have at the end of today's presentation. As the questions continue to come in, please note that an evaluation survey link will be available shortly in the chat box, and this link will also be emailed to you following the webinar if you logged in using your email address. We encourage you to answer the evaluation and give us feedback, as we intend to listen to the feedback and improve our webinars whenever we can. In fact, this webinar series came from suggestions from our audience. If you logged into today's webinar as anonymous, we encourage you to access that evaluation from the chat before the webinar ends. Okay, Terry, we have several questions, and I'll deliver them to you, and then I'll be publishing them on the Q&A box. So first up, have you used USGS's R package, EGRET, E-G-R-E-T, Exploration, which stands for Exploration and Graphics for River Trends?
You know, I have heard of this package. I haven't used it directly before. I've seen some demonstrations of it, and it looks like they've got some great tools. So definitely would suggest if this intrigues you, if you'd like to do some more advanced things with discharge data and with streams and rivers in general, that would be another great package to highlight and to check out. So thanks for bringing that one up. I know I included a non-comprehensive list of extension packages and things that you might want to use, but EGRET would be another great one to add to that list.
Yeah, I think for those of us who are learning alongside, learning from you, this is opening up the many I can just imagine how many packages and tools there are.
It's very exciting, but can be quite daunting. So it's often really useful to think about what your specific question is, and then finding something that you can really hone in on to answer that question or reach a specific goal. The thing with R is that the possibilities are endless. So really thinking about kind of how to work things in with your needs and working things in sort of piecemeal as you increase your skills is a good thing to do, just to avoid the overwhelmingness of all of the available packages.
Right. Thank you. Okay, next question. How do you find the documentation for notation in DF outputs? I don't know. I don't know if DF is discharge flow or what. Maybe you know what that's referring to, but I'll start again. How do you find the documentation for notation in DF outputs for different sources, e.g. USGS, IDEM, so that you can understand the codes in the DF and determine characteristic information? This person's been struggling to find this documentation since last session.
Yeah, that's a good question. If I have a moment, I'll try to post it in the chat, and maybe we can shoot an email to the attendees, or I can maybe put it in the GitHub. I know of several links that have like comprehensive lists of codes. One thing I will note is in some of the data retrieval vignettes, there are some good tables of really common codes, like things like discharge and stage and what the statistics are if you want mean versus max and things like that. So I know there are some more curated lists through the data retrieval vignettes and guides and things like that, but I know I do have access to a more comprehensive list of them, which I'll plan to add to the GitHub, and potentially if we have a way to get in touch with everybody who is registered for that, to send that around, because yeah, it does take a little bit of internet sleuthing, particularly if you're after something that's a little more rare than something as common as discharge. Yeah, that's a really good question, and yeah, something that has been tricky as these tools expand to really keep the documentation, in line with how rapidly we're actually having access to analyze the data. So yeah, good point.
Okay, thanks. Next question is down in the weeds, is on one of your code lines. What is stat equals identity with geom bar doing? So I'll publish it so you can see this.
Yes. So I need to find that. Okay. So remember when let's go back all the way to plotting water year versus peak discharge. So if we want to create a bar chart, we can, let's see if it'll do it if I actually plot it without, oh, no. So in this case, we actually want R to say, okay, I would like to look at Eno recurrence, and then I want it to actually plot peak discharge as the number in each bar. So that's where you just say, I want, if we're looking at peak discharge, I want R to plot the identity of that specific cell in the data frame as the height of the bar. Some other stats could be count. You could, count the number of occurrences of a given number. If you're thinking about something like a histogram, a stat equals count might be helpful there. But in this case, it's just saying whatever the identity is, whatever the value is of that specific cell within the data frame, it's going to plot that as the height of the bar. Yep, that's a good question. And yeah, my apologies for skimming over that as we went through.
Okay. You went to it pretty quickly, Kateri. That was, I'm like, can she find this? Okay, next question. Are scripts available that allow for more advanced flood frequency options of Bulletin 17B, such as specifying regional skew values?
That is a good question, and that is a question that is perhaps above my pay grade. I am not a trained hydrologist. I have learned how to do a lot of these things that are useful as they pertain to water quality. But I think some of these more specific things like regional skew values, they may be available through some of these packages like LF-stat and ecohydrology. The functions that we saw today are not the only functions that exist in these packages, but some of those more specific applications may be things where you might need to actually create some R code on your own, just given how some of those tools may be more widely used than others. So definitely recommend looking through some of these packages that we either worked with today or mentioned in the PowerPoints to see if maybe some of those things exist in those packages. But if not, it might be worth sort of thinking through what are the mathematics of actually calculating those things on your own, and then you could maybe implement those as a standalone function yourself. But yeah, my apologies. I don't know off the top of my head how to work with some of those specific metrics.
Okay. Next question. This is about masking. Just a suggestion. You can also avoid masking functions by specifying package name : function.
Yes, that is a really useful tool. So if you have two packages that are using the same function name, and perhaps you've loaded them in a specific order, so one of them is masked over the other one, you can say, dplyr, I want to use the dplyr filter function, and maybe there's another package that uses the filter function. So that's a useful tool if you are dealing with packages that include masking. The issue with ecohydrology specifically is it will mask this the dplyr pipe function. And so in this case, we're not actually we can't say dplyr : pipe. And so for this case, the colon workaround doesn't function quite the way that we would need it to in order to work with the pipe. So that's why I did recommend uploading or loading in ecohydrology before any other packages for that specific issue that pops up. So that's just one thing to point out, but that is a really great option to use throughout your regular coding life. So an example of that, if I'm using my group by function, I believe this is dplyr. So you could say dplyr : group by. So this will call a specific dplyr function called group by. If you don't say what package it is, it'll just assume whatever is sort of the default of what's being used right now.
Okay, thanks. Next question. How do I modify the code to use ecohydrology instead of LF-stat baseflow?
Yes, that is a good question. Okay, so if we wanted to use ecohydrology instead of LF-stat, we'd first have to load ecohydrology and make sure it's installed. So I'll trust that you can do that up at the top. But in this case, instead of using the function baseflow, we would use the function called baseflow separation, and maybe calling this eco or something like that. Then this should be the same since we're just using columns that already exist in our data frame. Again, you'd need to follow through if you've renamed it baseflow eco, go into baseflow stat. But basically, wherever you use the function baseflow, you would just substitute in baseflow separation. And then it should, as long as you don't rename things or you at least trace them through, you shouldn't have to change really anything else within this line of code, and I'm just verifying that here. Yes, because the rest of this is just working off of this initial calculation of baseflow separation. So again, if you renamed everything, instead of this underscore LF-stat, you could call it underscore eco or something like that. Then you just use this baseflow separation. So that would really be the only thing that you have to change, with the exception of any tracking of those column names throughout that section of code.
Okay. Next question, is it possible to have codes in Python?
Let's see, I'm assuming in general, there are lots of codes in Python. I'm assuming that wasn't your specific question. So for these specific codes that you saw today, these are our specific codes. In many cases, there are lots of parallel things that you can do in R and Python, where you could have a code that does the exact same thing in Python as you would get in R, and you could maybe output the exact same analysis or a spreadsheet that looks exactly the same. In this case, this isn't directly applicable, so you wouldn't be able to run this in Python, and it would be a totally separate session to actually develop the code in Python. But that's sort of a big theme of these webinars, is to think about what tools might be useful, what tools are commonly used. We'll have sessions in both R and Python that theoretically could be done sort of in parallel with both.
Right, and more on Python to come in the future sessions.
Yes.
Okay, there's a warning in R that comes up that the USGS site is changing next year. How will that affect the R package?
Yeah, that is a good question. So this is a good example of this. These are open source packages that are oftentimes are grabbing data from existing websites. So the great thing about these sources is that it's free. It's easy, it's easy to access if you know what you're doing. But the downside is that things can change over time, and so you need to be nimble and make sure that your code is still working as things change. So the specifics, I don't have off the top of my head, but these will be things that first, the documentation for these packages is typically pretty good. And so just keeping an eye out when these things do change, that you're looking for the new documentation of those packages. These packages are maintained by USGS and EPA. And so all of that documentation should be there online as we move forward. But be ready, these codes won't stay exactly the same forever. So yeah, just be aware of that. I'm bracing for that impact as well. So I'll be waiting with bated breath, just like you are.
Okay, just a couple more, Kateri. This is a pretty general one. Do I really need to have RStudio?
That is a good question. So I'll bring you back to when I was first learning R. I did not have RStudio. I used an R window. You can open up R software, and you can open up scripts. You can open up a console window. Everything will run just as we ran it today. You should be able to do everything in R alone without RStudio. So you don't necessarily need RStudio to use R. I don't know if I know a heavy R user that doesn't use RStudio, is the flip side of things. So RStudio has first of all, as you can see, it has a pretty nice user interface where we have our source section of the window, we have our console section, we have places for output, we have places for our environment. So it keeps it all in this nice user interface. It also has the functionality of things like if you're connected to GitHub, your window might not look like this, but mine is connected through GitHub, and so you can track things through GitHub. You can work from your terminal on your computer within your console window. So lots of sort of add-on and additional user interface tools that are available in RStudio that are not available in just base R. So that's sort of the benefit here, is that you can use R just plain, but there's this really nice user community that is built up around using RStudio and this nice user interface that really does save time and energy and things like that. It also has really nice color coding, which I really appreciate, not being a computer scientist by trade. So I really like the color coding and things like that come along with that user interface.
Hey, have you used discharge coupled with water quality concentration data, say for nutrients, to calculate loads?
Yes, so that would be kind of the next step of this. Is we had our water quality session, we've had our discharge session, and so basically, if you multiply concentration by discharge, you get load over time. And so that's where kind of the next step would be. We won't be specifically covering that in this webinar series, but that's sort of our next logical step in running these analyses. One thing you might need to think about is if you're not measuring water quality continuously or daily, like we have for discharge, you would want to think about how you would marry those two sources of data with daily discharge and maybe say monthly water quality data. Do you do you want to interpolate your water quality data so that you do have an estimate for daily? Do you want to think about how you would apply, how you would aggregate your discharge up to, say, monthly values and things like that? So all sorts of sort of temporal considerations when we do have these different data sources that are collected either on different scales or with different tools. Some of them are automated, some of them a person has to be out in the field to get them. So yeah, I'm sure I could continue talking about that for hours at this point, but that's sort of the next step is to work with these to calculate loads.
Hey, a couple just came in. This person says, I have the most current version of R, funny looking kid, R version 4.2.1, close paren, and am not able to install the eco-hydrology package. Keep getting message, package eco-hydrology is not available for this version of R.
Yes. So the new version of R has come out. I am currently still working on the previous version of R because I have a few projects that I need to wrap up with this version specifically. So I have not upgraded yet. Again, like I mentioned, these things are sort of constantly shifting under our feet in terms of the versions of R, the versions of packages, how to tie those together. So one thing to point out is that as our versions change, some of these packages are no longer supported on CRAN, some of them are supported on CRAN. But the nice thing is when you do have documentation for these packages, you can install those yourself. And let me try to pull up I'm going to try to pull up a specific tool or a specific guide how to install. I might not be able to do this live, but I'll try to put it in the chat as we're finishing up. Or even if you Google it, how to access a version of or a package in R that's no longer on CRAN. So that's one thing to point out. And my apologies as things have shifted as we've been developing these webinars. Is that yeah, a few of these packages haven't been working as well as I had anticipated.
Hey, so I think that's okay. That's okay because we know that's instructive to those of us who will have that same problem pop up. So. Okay, last question. Does CRAN plan on having a new package to replace LFstat?
So CRAN and the developers of packages are separate entities. And so CRAN is the package repository, and there are certain requirements for packages to be supported by CRAN, specific documentation, specific style of code, things like that, where if you get a package added to CRAN, those are the requirements. Those requirements may change over time, they may be updated over time, and so some of these packages that were developed earlier on may be depreciated in new versions of R. So LFstat was developed by a specific group that for whatever reason is no longer supported on CRAN. The code is still available on GitHub, and so how you're actually able to access that in the new code that I showed today is that you could use this DevTools function or DevTools package to install an old version of LFstat. And so that's how you get around. You can access all of these packages from CRAN directly, or you can grab them from a GitHub repository that someone just has. So those are some options to get your packages into your library individually.
Okay, that's all the questions, Kateri. Thank you so much for a great presentation and a great QA session too.
Yeah, thanks everybody.
Yeah, so let me have a few closing remarks here. As I mentioned earlier in the webinar, should you have any additional questions for Kateri, or if your question today was not answered, which I think we did get through all the questions, but maybe you still have a question, please feel free to contact Kateri after the webinar. Her contact information is included on this slide for anyone who would like to get in touch. Okay, you can find information on future webinars as well as a recording of today's presentation on EPA's Water Quality Modeling Workgroup page. The link to that page is also shown at the bottom of this slide. As a reminder, you can find a link to an evaluation in the chat pod. We encourage you to answer the evaluation and give us feedback on making improvements in the webinar series. Additionally, if you would like to receive updates on the webinars, please sign up on the EPA website on the About the Office Water page. navigate to the Subscribe to EPA's Water News link found in the green Related Information box on the right side. Select the Modeling Webinars email list for these webinars and feel free to add other topics of interest. The link can be found on this slide, as well as in the chat pod on the right of your screen momentarily. As a reminder, you will be sent an email with a certificate of attendance. If you have logged into this webinar as anonymous and would like to receive the certificate, please email our technical support. The technical support email address is in your registration confirmation email and is posted in the chat box. At this, I'd like to conclude today's webinar. Thank you so much, Kateri, for an amazing effort today. And of course, thanks to everyone who joined us. That ends our webinar for today. So thank you again, and we'll see you next time.